1 in 3 Australian men and 1 in 4 Australian women will be diagnosed with cancer before the age of 75. Cancer is one of the leading causes of death in Australia, with an estimated 45,700 people passing away each year. As stated by the Cancer Council of Australia, 1 in 3 cancer cases are easily preventable, with the most effective means of prevention being early detection. Treatment of cancers detected in their early stages is likely to be more effective and thus has a higher chance of being successful. Upon passing diagnostic evaluation, patients are subject to screening tests of different types, depending on the tumor location and size. Microscopic imaging methods are used in the study of biopsy samples to provide structural and functional information, whereas X-ray imaging and MRI, magnetic resonance imaging, provide images of living tissues at the macroscopic level, but at a much lower resolution. High-resolution techniques for subsurface imaging of tissues that could provide detailed information related to early detection of cancer near the surface of the skin are not currently available. One of the biggest unsolved problems concerned with medical imaging is how to combine macroscopic and microscopic technologies so that the precise characteristics of cancers can be outlined. A more recent screening technology, implementing terahertz radiation in the detection of abnormalities near the surface of the skin, has shown promising results. Terahertz radiation is powerful enough to penetrate skin on a subsurface level, but is not strong enough to damage tissues. However, contrary studies have demonstrated that cell exposure to terahertz radiation has stimulated morphological changes in cellular structures, and even cell death at extreme cases. Thus the question is raised, does terahertz imaging have the potential to be implicated as a means of cancer diagnosis? As previously mentioned, there is a variety of scanning technologies that are implemented in cancer detection. These range from CT scans, nuclear scans, ultrasound, to MRI, PET, and X-ray scans. Most scanning technologies function by radiating electromagnetic energy through a patient, which is situated above an electromagnetic detector. Waves travel through the body and are absorbed in different amounts by different tissues, depending on the radiological density of the tissues they pass through. The electromagnetic detector is exposed to varying degrees in different places, thus creating an image. Bone contains calcium, which has a higher atomic number than most other organic tissues, thus they produce a high contrast on the electromagnetic wave detector. Soft tissues with smaller atomic numbers, which mainly consist of carbon, hydrogen, nitrogen, and oxygen, appear as a darker grey tissue on the image. Depending on the intensity of the radiation, cancers may appear as dark spots or round nodules. Unfortunately, due to the high photon energy of most of these technologies, they carry with them potentially serious repercussions. CT scans have shown to expose patients to up to 100 times the radiation experienced through a single X-ray scan. A heart scan, for example, increases the risk of lung cancer, while a head scan raises the risk of thyroid cancer. The spectral region of terahertz radiation is the key factor in representing an opportunity for its application in medicine. The terahertz frequency region occupies a large portion of the electromagnetic spectrum between infrared and microwave radiation regions, ranging from 1 mm to 0.1 mm in wavelength, and ranging in frequency from 3.0 times 10 to the 12 to 0.3 times 10 to the 12 Hz. The photon energy of terahertz radiation is several times below the energy level required to ionize or remove valence electrons from biological molecules. Thus, terahertz radiation is classified as a type of non-ionizing radiation. This is crucial as non-ionizing and ionizing types of radiation generate vastly different effects in biological structures. The presence of cancer typically causes increased blood supply to affect tissues, and consequently a local increase in tissue water content is observed. This increase in water acts as the natural contrast mechanism for terahertz imaging in cancer detection. Terahertz wave generation is split into two general classes, continuous wave and pulsed wave. Continuous wave systems can be produced by approaches such as photomixing, which is the generation of continuous wave terahertz radiation from two lasers mixed together and focused onto a photomixer device which generates the terahertz radiation. Free electron lasers, a unique type of laser generated through the feeding of high-energy electrons from an electron accelerator, and quantum cascade lasers, which are semiconductor lasers that emit in the mid to far infrared portion of the electromagnetic spectrum. Pulsed wave terahertz radiation is generated via methods such as ultrafast switching of photoconductive antennas and the rectification of optical pulses in crystals. When a terahertz radiation wave is incident on a target, an array of pulses will be reflected back from the various points of contact. For each pulse detected in the signal, these amplitudes and timings are different and can be measured precisely. The principle of time of flight technique, similar to LADS and other depth perception technologies, is used to estimate the depth information of the target through the time that is required to travel over a certain distance. Similar to X-ray continuous wave imaging, the filtered back projection algorithm is applied to construct 2D and 3D images of the target. As with any technology, there are both pros and cons to terahertz screening. As mentioned previously, studies have shown terahertz radiation to have little photon energy, thus causing it to be a form of non-ionizing radiation. Consequently, terahertz imaging does not pose any ionization hazard for biological tissues. Terahertz radiation is also very sensitive to polar substances, such as water. Thus, terahertz waves can provide better contrast between softer tissues than scanning technologies such as X-rays can. As the terahertz wavelength photon energy is relatively low, less energy in comparison to other screening technologies is required in the process of generating terahertz radiation. This makes the technology favorable in terms of convenience, with the ability to carry out the scan via portable handheld scanning devices, thus rendering the process affordable, convenient, and painless. Although terahertz imaging is subject to an area of competition in terms of screening technologies, which have proven to be fast or deeper in terms of subdermal penetration, none of these technologies preclude terahertz imaging from finding its own niche, as there is no technique that can clearly distinguish benign from malignant lesions, macro and microscopically. The high sensitivity of terahertz wavelength to skin moisture is a key indicator in clear imaging techniques, with competing technologies such as high-resolution MRI being less convenient and more costly. Terahertz imaging, when compared to adversary technologies, falls behind in both speed and image registration. Long measurement times in specific areas of the body may render the accurate detection of healthy and diseased tissues challenging. Additionally, the slower the measurement, the longer the subject has to remain still and in contact with the imaging window. Furthermore, specific studies concerned with adverse effects of terahertz radiation have shown that exposure can cause cellular proliferation, which is rapid growth, cellular stress, and in extreme cases, cell death. The fact that proteins react to terahertz radiation may have negative implications for human exposure. In summary, terahertz imaging has the potential to be a valuable imaging technique in the future, specifically in cancer diagnosis, primarily due to its sensitivity to water and overall accessibility in terms of its mobility and relatively low energy cost in production of the terahertz wavelength. However, the technology is in its early stages of development. Improvements in the terahertz imaging speed and the goal of developing a near video rate of imaging system for terahertz screening needs to be attained if the technology is to compete with other screening methods. Furthermore, more research is required in order to establish the long-term effects of terahertz exposure on proteins and cells in order to determine whether the technology is viable for long exposure scans. With more research and development, terahertz imaging can find its place amongst widespread screening technologies and contribute to the ongoing battle with cancer, potentially saving the lives of many.